Welcome to this comprehensive review. Today, we're embarking on a truly massive journey, literally, into the world of mechanical giants. You know, when we look at towering skyscrapers, sprawling toll roads, or those absolutely massive mining operations, it's so easy to just focus on the finished product. But behind every single mega project is a highly complex, high-stakes ecosystem of heavy equipment. In this explainer, we're going to break down the sheer scale of the heavy equipment industry. We'll trace the path of these multi-ton machines all the way from their economic market value through the incredibly tangled web of import logistics straight down to the precise engineering required on the construction site. It's a fascinating story of macroeconomics, high-risk logistics, and structural mastery.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the heavy equipment market potential, move right into procurement and import scenarios, tackle those massive logistics challenges, break down the occupational safety risk analysis, and finally, wrap up with construction optimization and engineering.
First up, Section 1, Potencia Pasar Alet Barat, or the heavy equipment market potential.
We're entering the first phase of our funnel here, which is the sheer scale of the market. Before a single scoop of earth is ever moved, these mechanical giants represent a massive economic driving force, especially in rapidly developing nations like Indonesia. Just take a look at this number. $3.62 billion. That is the staggering projected market value for heavy equipment in Indonesia by 2026. And to put that into perspective, that translates to an expected demand of around 25,000 units. These aren't just expensive machines, they are literally the backbone of national development. Every single infrastructure goal a country sets relies entirely on whether it has the mechanical muscle to pull it off.
Now, what's really interesting about this slide is where all these machines are actually going. You might hear news about governments cutting back on coal production targets, which you'd think would completely tank the heavy equipment market, right? Well, look at the data. Mining still dominates at nearly 47%, and that's heavily driven by nickel and strategic minerals. Right behind it, construction and infrastructure make up 37%. Massive national initiatives, like the new Nusantara Capital City project, the toll roads, the ports, they are eagerly absorbing any excess capacity out there. The demand doesn't disappear. It simply shifts to wherever the growth is happening.
Moving on to Section 2, Scenario Pengadaan dan Import, or Procurement and Import Scenarios.
So the demand is obviously massive, but how do companies actually get their hands on these multi-ton giants? Importing heavy equipment is vastly more complex than bringing in standard consumer goods. You can't exactly order a bulldozer online and expect two-day delivery. First off, a company needs an NIB, a business identification number, and an APIP, which is their importer identity. Then comes rigorous technical verification from various ministries. After that, an independent surveyor has to inspect the machine before it even gets on a ship, just to issue an LS, or surveyor report. Only then can it face the final hurdle of PIB, which is customs clearance. It is an intensely monitored, highly strategic process.
And, that process changes drastically depending on the age of the machine. Importing new equipment, it's relatively smooth sailing. The focus is mainly on technical specs and basic safety. But used equipment? No way. That is highly restricted. The government scrutinizes second-hand imports heavily because they carry severe environmental and safety risks. To bring in a used machine, you need special recommendations from the Ministry of Industry or Energy, and those surveyor quality checks are incredibly unforgiving.
Because buying these machines outright requires massive upfront capital, a lot of contractors turn to the highly lucrative rental market. This chart really breaks down the economics nicely. You can easily see why a mid-sized contractor would much rather pay around 60 to 100 million rupiah a month to rent a 20-ton excavator instead of dropping upwards of 1.2 billion rupiah to buy a used one. And that's not even factoring in the ongoing maintenance costs. Renting just provides so much more flexibility for project-based work.
So the crucial point is understanding how this rental ecosystem actually operates. It generally splits into two main models. You have wet rental, which means you're hiring the machine, the fuel, and a highly skilled operator. It's definitely more expensive, but the rental company retains tight control over their asset. Then there's dry rental, which is just the machine itself. It's cheaper for the contractor, but it carries a significantly higher risk for the rental company. Why? Because an unskilled client operator could easily damage a machine worth billions of rupiah.
All right, let's shift gears to Section 3. Menaklukkan Tantang Logistik, Conquering Logistics Challenges.
Now that the equipment is procured or rented, we face a monumental physical challenge, actually moving it.
You don't just drive a massive crane down the toll road. We are dealing with extreme dimensions and weight here. This requires custom transport trailers, special road permits, and meticulously planned routes to avoid things like low bridges or weak roads. Plus, despite being heavy machinery, the internal mechanics are surprisingly sensitive to vibration and damage during transit. And timeliness? It's everything. A delayed excavator means an entire construction crew stands idle, causing this massive domino effect on the budget. This is exactly why specialized logistics partners like Essilogos utilize advanced digital fleet management systems to ensure these giant assets are tracked and arrive safely precisely on time.
Moving right along to Section 4, Analysis Risiko Keselamatan Kerja, or Occupational Safety Risk Analysis.
Okay, so we finally arrived at the construction site. Now, our focus completely shifts to the human element, which absolutely must be managed with absolute precision. To do this, engineers employ sophisticated methodologies like HAZOP, that's the Hazard and Operability Study. Now, while this systematic method is super common in the oil and gas industry, its application in construction is proving to be vital for spotting complex risks early. It doesn't just list out dangers, it looks at normal work procedures and uses specific guide words to imagine how things could go wrong, like what happens if a heavy lift is delayed, or if an excavation trench is dug deeper than planned.
And this brilliantly illustrates how those deviations are quantified. Engineers use a risk matrix. Every potential hazard identified in the HAZOP method gets plotted right here based on its likelihood of happening and the severity of its impact. By plotting risks on this grid, project managers can instantly visualize which activities fall into the low, moderate, or critically high-risk red zones. That allows them to prioritize their safety resources exactly where they're needed most.
Let's look at a real-world application of this from the Stadion Teladan project. Using HAZOP, they identified a bunch of high-risk activities. Digging deep excavations near live power lines, that posed a severe threat of electrocution or collapse. They also found that delayed heavy material lifting, maybe due to a sudden crane malfunction, created massive risks of dropped loads. Even simple, everyday deviations, like insufficient use of PPE during concrete pouring, were plotted as moderate to high risks. Identifying these things early allows for strict protocols to be enforced way before a tragedy can occur.
And finally, Section 5, Optimize dan Rekayasa Construction, or Construction Optimization and Engineering.
For our final segment, we're zooming all the way into the highly technical engineering required on these megaprojects. Let's look at the earthworks phase of the Sleman Stadium project. By calculating incredibly precise productivity rates for their excavators and bulldozers, factoring in exact soil types and terrain, the engineers ran multiple trial and error calculations just to find the perfect mix of equipment. The result? Absolutely wild. A staggering 64% reduction in the time needed for excavating and filling, and a 24% savings in costs. Proper heavy equipment management isn't just about having the machines on site, it's about choreographing them perfectly.
But earthworks are really just the beginning. When it comes to building large-span roofs from massive stadiums or airport terminals, the heavy lifting becomes incredibly complex. This requires erection engineering analysis. You see, in megaprojects, the sequence of building cannot be separated from the structural design itself. An unfinished roof might not even support its own weight. Every single step of the assembly, as those giant blocks are lifted by cranes, must have a verified load path and a guaranteed margin of stability.
Let's move to and see how this builds out in reality, looking at the specific methods engineers choose to lift these giant components. They have a whole toolkit of strategies. Element erection basically builds it piece by piece up in the air. Block erection pieces things together on the ground first, which really reduces dangerous high-altitude work. For the absolute most complex roofs, they use the lift-up method, employing powerful strand jacks to haul massive, pre-assembled structures into the sky all at once. Or if vertical lifting is somehow restricted, they might assemble the roof on one side and literally slide it into place. The choice depends entirely on the site's logistical constraints and the crane capacity they have available.
Which leads us perfectly to a core finding from recent construction optimization research. I'll read this directly because it's absolutely crucial. Large-span roofs are rarely erected safely and efficiently without explicit erection engineering analysis and carefully designed temporary works. Treating these massive heavy lifts like a simple delivery schedule, just moving a piece of metal from point A to point B, rather than treating it as a profound structural engineering challenge, is exactly what leads to catastrophic failures. The temporary supports holding everything up are just as important as the final bolts.
And that leaves us with a pretty critical question to think about today. The scale of our ambitions is only growing.
From multi-billion-dollar economic markets down to the millimeter-perfect engineering of a heavy lift, we are constantly pushing the limits of what's possible. So as our mega projects grow ever larger, will our logistical networks, our safety protocols, and our engineering foresight evolve fast enough to safely tame the mechanical giants we so heavily rely on? It's a delicate, ongoing balance between rapid infrastructural ambition and harsh operational reality. Thank you so much for joining me on this explainer, and keep questioning the mechanics behind the world around us.